It's Kurt Beschorner, and the name of my talk is Footwear for Prevention of Human Slips, from Friction Mechanisms to Ergonomic Solutions. First, I want to thank the committee for this invitation. I'm very honored to be here and to be able to share our research. So I'm the messenger, but this work is done by lots of people. I want to especially acknowledge my students who make this research happen, as well as my collaborators. And in particular, I'll point out Sarah Hemler, who is presenting this afternoon. So my talk's going to have 4 sections. I'm going to start by talking about the problem of slips and falls. I'll talk about 2 mechanics pathways in which footwear influences friction. The first is hydrodynamics, and the second is hysteresis friction. And then lastly, I was asked to think about where this field should be going, so my last section will be to discuss that. So falls are a big problem. This is data from the United States for reasons why people end up in an emergency department. So on the left are disease-oriented reasons, and on the right are injury-oriented reasons. And you'll notice that falls are the second most common reason overall, and by far the most common with regard to just injuries. Now, of course, everybody here knows that falls are a big problem. What I find that's particularly interesting is even my kids understand that falls are a problem. So my 6 and 4-year-old shown in this picture, just last week they were running around on our hardwood floors, and our 6-year-old yells to our 4-year-old. She says, "Max, you have to take off your socks or you're going to slip and fall." And so I was curious, how do my children know that this is such a big problem? And I started noticing in their books, there are just lots and lots of cases of falls. So this is Cat in the Hat, when all the things fall. And then this is one of Richard Scarry books. Richard Scarry loves to write and illustrate about falls. So falls being a big problem is something even my kids can understand. Falls also lead to severe injuries. So the median time away from work is 10 days for falls, about 25% longer than it is for all injuries. And then falls account for about 1/3 of all the fractures. Of course, my kids know this as well because they've read the book After the Fall, which chronicles Humpty Dumpty after his great big fall, and including his physical recovery and his psychological trauma. So in this picture, he's too afraid to climb back up to his bed, so he's sleeping on the floor. As Richard mentioned earlier, the events that cause a fall are dependent on the population, and so our research is particularly interested in slips. So I'll highlight that part of these graphs. So on the left, we have occupational falls, and slips are believed to be right around half of all of the non-fatal occupational falls. If we look at falls among community-dwelling older adults, so generally the healthy segment of the older adult population, slips are about 1/4 of those. But if we look at more the frail portion of the older adult population, we'll see slips are just a very small segment of those. So our research is particularly relevant to able-bodied adults. And footwear can make a big difference. So this is a study we did where we gave people different footwear. All of the footwear was called slip-resistant. And then we exposed those people to an oily floor surface. And so you'll notice for one of these shoes, the slip rate is right around 80%, whereas for another shoe, nobody slipped at all. And so the type of footwear can make a big difference in somebody's risk of a slip event. However, my kids know this too, because they watch a show called PJ Masks. And in PJ Masks, there's a character named the Gecko, and the Gecko has a superpower, which is super slip-resistant feet. So when Gecko's friends are incapacitated by slippery floor surfaces, Gecko can save the day. So slip-resistant feet is a superpower. And so we know clearly that slip and falls are a problem and that they are preventable, specifically through footwear. And this is something that is both empirically true through the data, but also intuitive to the point where children can understand it, and it shows up commonly in children's stories. Now, where there is not consensus is how do we design shoes to have good friction? And there's not consensus among footwear manufacturers, there's not consensus among ergonomists, and there's certainly not consensus among the general public. And so this is an area where we've tried to add some clarity to. And so our group uses 3 competency areas. The first is mechanics analyses, including biomechanics as well as tribology. The second is understanding of human motion, and in particular human gait. And the third is ergonomic interventions to translate our findings into useful pieces of information that can be applied. And so I'm going to be talking about engineering or shoe floor friction mechanics throughout my talk. So I thought I'd start with just outlining a structure for how we characterize shoe floor friction mechanics. So if we start with dry sliding, there's 2 kinds of friction. The first is adhesion, and the second is hysteresis. And so as we know, shoe and floor surfaces are both rough, and they come into contact in certain regions where the asperities come into contact. And so where that contact happens, there are intermolecular bonds that are formed between the 2 surfaces, and to break those bonds during sliding, so as the shoe slides relative to the floor, requires force to break those bonds, which is known as adhesion friction. The other kind of friction is hysteresis friction, and so hysteresis is a material response in shoe materials. And the force required to overcome that material response is known as hysteresis friction. And so there are 2 ways that a fluid can interrupt these kinds of friction. The first is in boundary lubrication. And so in boundary lubrication, a liquid that coats the flooring and the shoe surface basically disrupts these intermolecular bonds from forming and reduces adhesion friction. And so we typically find that longer molecules like oils achieve more disruption of that friction than shorter molecules like water. And so in the case of boundary lubrication, where adhesion can be disrupted, hysteresis friction becomes very important. The second is in mixed lubrication. And so in mixed lubrication, which is for tires is sometimes called hydroplaning, the fluid between the shoe and the floor surface becomes pressurized, and it basically forces those 2 surfaces apart. And so this fluid pressurization, or hydrodynamics, or mixed lubrication, this is really problematic because it disrupts both adhesion and it disrupts hysteresis. So we think an appropriate strategy for enhancing footwear friction is to increase hysteresis friction and reduce fluid pressurization. And so that's going to be how I organize most of this talk. Before I get into that, though, I know people are in this group are really interested in friction measurement methods, so I thought I'd just briefly touch on how we do our coefficient of friction testing. And so we're guided by concepts that coefficient of friction testing should be biofidelic. So we've published some research on the dynamics of slipping. And we've noticed three important things during that research. The first is that the foot never stops slipping from the moment it hits the ground until after the slip. And we found that typically the sliding speeds are over 0.3 meters per second for this entire duration. The second is that when the foot starts to slip forward, the shoe floor angle is between 15 and 25 degrees. And so the heel region is particularly relevant to slip resistance. And the third is that the force is right around 150 to 250 newtons at the moment that the foot starts to slip. So the forces are quite a bit lower than body weight. And so we developed a test method that aims to be biofidelic, that incorporates what we learned from the biomechanics of slipping. And we tested this test method against 124 human slips that were collected in our laboratory with 9 different designs of footwear. We use a method called area under the curve, which is a common method for assessing diagnostic tests based on their sensitivity and specificity. And so this is a 0.5 to 1 scale, where 1 indicates your test gives you perfect predictions, and 0.5 represents that your test is worthless, basically. And so our test comes in at 0.82. What we think of as the industry standard in the US is the ASTM F2913. That standard came in at about 0.7. So we feel pretty good that our test method is giving us pretty appropriate data. And so, as I mentioned previously, I'm going to be talking about fluid pressurization and hysteresis friction. So I'm going to start with fluid pressurization, and so this is fluid pressures across or between the shoe and the floor surface. And so fluid pressures have long been hypothesized to be relevant to slipping, dating back to the 50s and 60s. And so one of the things that we decided to do about 10 years ago was determine, can we measure this? So we drilled a hole in the floor surface, and we put a fluid pressure sensor in the floor surface so that the top of the sensor was flush with the floor. And we started sliding shoes over that fluid pressure sensor. And so every time we would slide a shoe over the sensor, we'd get basically a line scan of the fluid pressure. And so we found that if we did multiple scans, we could map the fluid pressures across the shoe's surface. And so here's an example of this. And so in this case, we have a shoe where most of the tread has been removed from the heel. The only exception is there's this one groove, which is called a flex groove, where we could not remove the tread. And what we found was that we find fluid pressures on either side of that tread groove. So we're finding fluid pressures in the locations of the shoe where there is not tread, which makes sense. And so we started thinking about hydrodynamic theory. This is the Reynolds equation. It's a complicated partial differential equation that's kind of a pain to work with, but fortunately it can be solved for different scenarios, including for a 3D inclined bearing as well as a 2D inclined bearing. And one thing we noticed in these tests is that so these equations have H, which is the film thickness, and PM, which is the maximum fluid pressure. And so both of these, a higher value indicates more separation between the surfaces, which is lower friction. And so we found that both of these terms are sensitive to the size of the bearing, basically. So in the case of H for a 3D inclined bearing, it's BL squared. And in the case of maximum pressure for a 2D inclined bearing, we have this L term. And if you solve these equations for lots of different scenarios, you'll often find that it's very sensitive to the size of the interacting surfaces. And so we thought, well, what happens during shoe wear? So when shoes wear down, typically you get one region of the shoe that will wear out first, usually at the corner of the shoe, and then the size of that worn region will grow as the shoe continues to wear. And so we thought, well, the size of the interacting surfaces is supposed to be really important according to theory. What if we measure the size of the worn region as the product of the width of the size of the worn region and the length? And so we started doing that. We've done this. We've done this in numerous contexts. I'm going to show one of the contexts. So what you're going to see is you're going to see a human participant who's walking across the floor surface. In the middle of the screen, there is a liquid contaminant. That liquid contaminant is placed on top of 30 fluid pressure sensors that are embedded in the floor surface, which allow us to measure fluid pressure as the foot slips across the surface. I'll show that again without the deafening sound. Or maybe not. But from this study, we were able to connect the size of the worn region to the fluid pressures. And so I should first say that we've done this in about 2 or 3 different contexts. My student Sarah has a lot of work where she's tracked the same shoes over time and gets very clear results. But what I like about this graph is these are all different kinds of shoes in this study. We have tennis shoes, we have running shoes, we have work shoes, we have slip-resistant work shoes, we have not slip-resistant work shoes, we have totally worn out work shoes, we have brand new work shoes, and you still see, even with all of that variability, you still see a clear trend between the size of the worn region and the fluid pressure, which is on the y-axis. So in this graph, the gray are slip-resistant shoes, the black are not slip-resistant shoes. Both slip-resistant and not slip-resistant fall on the same curve. The second thing we did is we determined, all right, can those fluid pressures that we measure during a human slip, do they relate to the coefficient of friction performance of the shoe? And they do. So increased fluid pressure is associated with a reduced coefficient of friction, just in the direction that we'd expect it to be. And so we said, all right, well, what's an easy test that people could use to measure the size of their worn region? And so after thinking about lots of different potential tools, we settled on a battery. And so we've tested 2 different size batteries, AAA and AA. And basically the way this battery test works is if the worn region is smaller than the base of the battery, then it passes. And if the worn region is larger than the base of the battery, it fails. Now many of you may notice that a lot of shoes, even in new condition, have tread lugs that are larger than a battery. And so we've started by applying this model to slip-resistant shoes, which tend to have very small tread features. And so here's data on shoes that failed versus passed the test. So the first thing you'll notice, so on the left is the AAA test, on the right is the AA test. Both of them show differences between shoes that failed and passed. So the shoes that failed the test have higher fluid pressures during a human slip than the shoes that passed. And then this is data from a separate experiment of longitudinal data, so where we've tracked the same shoes over time. And so this is during the pass condition, so before the shoes failed the test, and then this is during the fail, so after the shoes had failed the test. And we've done this both with mechanical wear, where we've worn down shoes in the lab, which is the black lines, as well as natural wear, where people have worn their shoes out in the workplace. And you'll notice that for every single shoe, going from pass to fail is associated with a reduction in coefficient of friction. The average reduction is right around 30%. Okay, so that's sort of the fluid pressurization. The second side of it is hysteresis. So I only sort of briefly mentioned what hysteresis was earlier. I'm going to explain it in a little bit more detail. So rubber materials, when you load them and you unload them, they follow a stress-strain curve with a component to it known as hysteresis. And so basically when you push on a rubber material, it requires more force to deform it than what's released when you let go of it. And so when you push on the material, it follows that light blue line, and then when you unload it, it follows that gold line. And so I'm going to show how this sort of mechanical behavior influences a piece of shoe material as it slides relative to the floor surface. So we're going to follow this one piece of shoe material. It's color-coded to follow these two lines on the curve. And we're going to watch what happens to this piece of shoe material as this floor asperity slides relative to the shoe material. So it loads along the light blue curve, and then it unloads along the gold curve. And so because it takes more energy to load the shoe material on the right side of the asperity than it unloads on the left side of the asperity, we get high pressures on the leading edge of the asperity, and we get relatively lower pressures on the trailing edge of the asperity. And so the differential between those pressures is, it gives us this hysteresis force. So this is a mechanical behavior, which means it's something we can model with finite element analysis. And so so my grad student, Pevand, created this multi-scale finite element model where he has this microscopic model which simulates rough shoe materials relative to rough floor materials. And he noticed that when running this model, the coefficient of friction value was sensitive to the pressure, so the amount that he was pushing down on the floor surface. So what we do with this model is we output coefficient of friction as a function of the contact pressure. And then we use the whole shoe model to model the contact pressures across the shoe surface. And so from that model, we get both the pressures and the areas of the regions in contact. And so with all that information, we're able to combine the information from the microscopic model with information from the whole shoe model to get an overall estimate of the coefficient of friction for the shoe. And so this is results from our models. This is results, experimental results. We have 8 different shoes and 2 different floor surfaces. And so the correlations are very good. The raw values are not perfect. Our model has a much narrower range than we see experimentally, but we were pretty pleased with the trend. And so we started using this model to understand what shoe design features influence hysteresis friction. And we noticed that, as I mentioned before, that the coefficient of friction is sensitive to the contact pressure. And so having a low contact pressure gives you a better coefficient of friction. And from our macroscopic model, we realized that this contact pressure varied across shoe surfaces and between shoes. And so you can have parts of the shoe that have a low contact pressure with an associated good coefficient of friction. You have sort of these yellow regions, which are not quite as good. And then you have these red regions, which are particularly bad. And so we started thinking, all right, what are some footwear design features that are related to contact pressure? And we came up with 3. The first is contact area. So if you distribute the load over a larger area, you can reduce the contact pressures. The second is shoe beveling. So as I mentioned before, the shoe is at an angle of about 15 to 25 degrees during the moment that it starts to slip. And so a bevel will better conform to the floor surface than a flat-heeled shoe. And so shoe beveling should be beneficial for reducing contact pressure. And then the third is hardness. So softer materials should be more deformable, which should reduce contact pressure. And so we created a statistical model based on just those three metrics while also controlling for flooring, because we use two different floorings. And what we found is that we could get really pretty good predictions of coefficient of friction based on three relatively inexpensive metrics of shoe design. What else was interesting is we were able to use contact area in particular, well, all of these metrics, as ways of diagnosing shoes with poor friction performance. And so these were two different shoes from the exact same manufacturer, so the exact same brand. The shoe on the left has a design flaw though. And so the shoe on the left has supporting structures behind the tread, basically these ribs that support it, two vertical ones and a horizontal one, as well as one that runs around the perimeter. And it has insufficient backing in these regions, which lead to these holes in contact area. Whereas this other shoe, in addition to being beveled, had a properly designed backing system, which gave it good contact area. And so our model predicted that the one on the right should outperform the one on the left, and experimentally we see that to be the case. So the one on the right performs about 40% better, thank you, than the one on the left. Okay, so I mentioned earlier that slip-resistant footwear is a superpower, so here are 5 steps to getting your slip-resistant superpower. The first is replacing worn shoes, and we propose a battery test for assessing the size of the worn region. The second, probably a lot of people have very expensive, very nice dress shoes, and what we often see with expensive, nice dress shoes are tread patterns that look like this. So purchasing shoes that have small tread features that are broken up by tread channels is important to alleviating those fluid pressures. The third is high contact area, and so you can actually identify shoes like this. If you push on that shoe, you will notice that there are these spongy areas. There are well-supported areas and there are spongy areas, so you can actually figure that out even at the shoe store. The fourth is a beveled heel. Beveled heels are good. Flat heels are bad. Beveled heels, our research found, give about a 15% better coefficient of friction than flat heels. And the last is softer materials. And we think that these recommendations are simple enough that certainly footwear manufacturers could implement them, but some of them even consumers could implement. All right, so I'm going to quickly go through areas that I see that could be interesting for future research. So the first is there are lots of methods for testing slip resistance, as people here know. In particular, there's, I think, three relevant methods for footwear. And so I'll just quickly point out the one in the middle. That's a commercially available test method that's based on the method that we've been using. I don't have any financial interests, in case anyone is wondering. But then there's that method. There's the Satcher device, the STM603. And then there's the ramp tester, which forms the basis for HSE's grip scheme. So in a lot of injury research, when diagnostic tools are developed, we go out and do a big prospective study where we track thousands of people and we look for health outcomes. But to my knowledge, That hasn't been done for any of these three devices. And I don't think it makes sense to do a separate study for all three. So one opportunity I see is let's put all these three tests up against each other on a big perspective study to assess their ability to determine who's going to experience a slip and who's not. All right. The second is one of the mechanisms that I ignored is adhesion. And the reason we've mostly ignored adhesion is it's really tough to model and predict adhesion. But there's been some work by Takeshi Yamaguchi's group that looks a little bit promising. As I said, it's complicated. You need to understand surface energies, which is basically the chemistry of the surfaces, and use that to calculate what they call spreading coefficient. So that's kind of like half of it. The other half is you need to know what the real area of contact is, which is really difficult to estimate. So they've started doing some imaging of contact area, which I think is really is pretty interesting. However, to get good estimates of real area of contact, you need to know what's happening at really small scales. And so we've started doing some research to look at surface roughness down to these very small scales, to the nanometer scale. Another area is surface characterizations. So I think Marcel is going to talk about this as well. And so he's done a lot of really great work related to flooring wear and cleanability and how that influences surface roughness. The other area that I think is also important is understanding these smaller scales. So the mechanics models of hysteresis indicate that in addition to micrometer scale and millimeter scale roughness, what's happening on the nanometer scale is also really important. And so I've started working with a material scientist who can unlock these new scales of surface roughness. And so on this graph, it's basically a power spectral density graph, where on the x-axis is the size of the asperities, and on the y-axis is roughness. And so we had these two floor surfaces that weren't behaving the way that we expected them to, based on profilometry data. But when we collected all this smaller scale data, we realized that the surface that these two lines intersected. So the roughness on the larger scales was not representative of the roughness on the smaller scales. And then another area is going beyond liquid contaminants. And so the Toronto Rehab Institute has been a leader in ice friction. But I think another area is soil mechanics. And so we've started looking into that a little bit. This is a video from underneath a floor surface of a shoe coming in contact. And so I should have slowed down that video. That's okay. But what we've noticed is that when we run these images, we see that contaminant gets trapped between the shoe and the floor surface. And so we think that tread design is likely really important for soil mechanics as well. And then the last thing is ladders, or sort of moving beyond floor surfaces. So ladder rungs, step edges, and other areas. And we are planning a new study, probably to start this summer, to develop a method for assessing shoe rung friction and validate it against human slips. So keep a lookout for it. And so I think through the research we've done and through potential future research that I mentioned, I think there's a lot of opportunities to prevent slips, prevent falls, prevent injuries. Which brings me back to Humpty Dumpty, because I don't think Humpty Dumpty wanted to be famous for his great big falls. I think Humpty Dumpty had great big plans, and I think if we're successful in doing this research and in preventing accidents, I think we have the opportunity to help people keep their plans. I want to thank our partners in research. I also want to thank our funders of research. please follow our research. I use LinkedIn and Twitter to share future research. Also, if you ever have a question or want a paper, please feel free to email me. Thank you.